Hello, good evening, everyone.
Good evening.
Uh,
Good evening, sir.
very low attendance. What's the reason? Yesterday also, I think it was the notification. I think you got like very late, I guess. But still, I got
Yes,
to know
sir.
that it was very less attendance yesterday also. But
We
it,
are not able to cop up this, no, 6 and 7. So we
uh,
are we are trapped with
Yes, sir. I also joined at 6.
we are
huh?
trapped in the 6 only.
You
Yes,
okay? So, are you able to now cope up with week 6 at least?
At least we
Not
6 SPD we are understanding. We are doing that.
okay.
Some
Week
time it will
6.
take to cover up
Okay. Week 6 is, I
because
think.
because, because
Uh,
we are in the quiz one, na, so we could not
yeah,
do
I
that
got it. Yeah, I
in
got it.
6 also.
I think week 5 also was there before the quiz one.
Yeah,
So
that's why the time was very critical and the course
correct, correct.
content was also different type of things. And
Yeah, yeah, I
it is
got it.
time taking actually. It is time taking. Everything is requires practice.
Yes. But I think week 6 was very much related to diagonalization, right? Uh,
SBD.
yeah, so that is singular value decomposition, right? So
And SBD is based on the diagonalization.
yeah,
Without doing week 5, you cannot do week 6.
yeah.
So we have to do week 5, then week 6.
Hmm.
So we are trapped with that. This is the reason. That's why. But still, we
But
have to
still,
do
why
week
the
6.
attendance is low? That is okay. So people are
Uh,
studying it.
no,
Is
no,
it
no. What
related?
happens now? When
Uh,
we come to week 7, no, then we
uh,
will not be able to understand anything. If
so
you don't do week 6, no, then it is, I think, it is
okay,
so.
but week 6 and week 7 are actually both are different. They are not related to each other at all.
Okay. Is it different? Then
Yeah,
it is okay.
so both week 6, week 7, both are the different entities, right? So they are not.
No, week 6 is dependent on the week 5.
Yeah, but week 7 is not dependent on week 6, right? Or
Okay,
yeah.
maybe.
So week 7 is principal component analysis, which is finding out the eigenvalues and eigenvectors. So okay, let us see what to do. Uh,
Okay.
I'll, I'll give you the gist of what is PCA is, and probably so I think in our syllabus for MLF, if it is concerned, PCA is only restricted to you know uh, dimensional reduction of two one-dimensional subspace. Okay, so let us try to understand. I don't. I think you guys have not gone through the lectures. Most of
Yeah,
you
we have.
possibly, right?
Honestly, we have not gone through that.
Yeah. Okay, fine. But we don't have much time to. So will have to
Yeah,
finish the,
okay, fine.
right. So we'll have to anyway start. You try to understand it. Maybe try to
Yeah,
focus here.
we will
Yeah.
see again. Oh,
Yes. So if you try to focus here also right now when I'm speaking, that will also help you. That at least if you can take 50% from this session, it will be good for you also. Then to relate much quicker, right? Okay.
eigenvalues and eigenvectors are the key
Yes.
pin
In
of
this,
this all this
yeah.
topic, right?
Right.
No?
Yeah. What is
Yeah,
it? Principal component analysis, right? So that is your uh, topic name, or this is okay. So we have, I think, when we have started. So I think, are you guys, all of you are comfortable with SVD, right? Maybe if you are not, I'll try to, if you get some time, if you want me to explain something, I'll try to explain it. Fine.
yeah, I want something.
Okay.
Once
Okay. So once
trivial.
it is, yeah, yeah. So I'll try to finish this maybe in 1.5 hours. And maybe the
Okay,
remaining time we can discuss with
okay,
SVD.
okay,
Okay.
okay,
Fine.
okay.
So principal component analysis, right? So first thing we have learned about two. What are the two main paradigms of machine learning? One is supervised machine learning and or supervised learning, and another is unsupervised learning, right? I think in the
Yeah,
week one, when I was talking about week one, we were discussing what are those discussions, or what are those topics which are there in supervised, or what are the algorithms which we see for supervised learning. There will be, I think, mostly we talked about two, which is regression and classification, right?
yeah, Yeah.
And why they are supervised learning, why we say them as supervised learning is because they contain label in the training data, right?
Level. Yeah.
With
They
input
contain level.
features, they have labels,
Level. Yeah.
right? And what is unsupervised learning? Uh, in the
We
training
don't
during
have.
yeah during training, we do not have in the training data set. We do not have labels associated with that input features, right?
Yeah.
That was the main difference between unsupervised and supervised learning. And there were two major techniques we have discussed, which are those: one is density estimation and another one is dimensionality reduction,
Reduction.
right? So this PCA is, it is an unsupervised learning algorithm, right? Unsupervised uh, learning algorithm. And another thing, what type of unsupervised learning it is? It's a dimensionality,
Reduction.
yeah, dimension reduction technique. Okay, it's a dimensionality reduction technique. So in the name itself, we can see what do you mean by dimensionality reduction. So let's say you have bunch of data points, right? Or when I say data points, what they mean to us physically. So what is the physical significance of data points?
Data points are the independent variables which
Yeah.
control function.
Okay. Correct. So, and they will contain the information, right? They
Yeah.
have those information. Can I say that they are the points which are which actually denote features, right? So each of the data point, let's say if x1 is a vector, if I
Yeah.
say it's a vector and it will have, let's say, n dimensions or d dimensions, what does that mean? How many features
D,
we are
D,
having?
data-
We
D
have
data
d
point.
features, right? So general our data set, how we try to look at this data set as, let us say you have maybe I'll just say that f1, f2, f3, and you have some numbers 1, 2, 3, right? So 2, 2, 4, 3, 3, 5, 4, 4, 6, something like that. So where is my x1? Is this one my x1? Right? So let's just say this is first data point, is the second data point, third data point, is fourth data point, right? And what is the so if I wanted this x1 in terms of a vector, how will I write it? Can I write it like this: 1, 2, 3, and so can I say that x1 belongs to which dimension? Three dimensions, right?
R3.
Yes, sir.
Right. So this is the way of visualizing it, right? So let us say how will, let us say we have these three features f1, f2 and f3. So how can I represent this data point x1? So it is a vector of points 1, 2, 3. So on f1 axis it will be 1, on f2 axis it will be somewhere 2, and f3 it will be 3. So can I say that this data point will be somewhere in the three-dimensional space, right? This data point is x1. Is that fine?
Yes, sir.
Are you able to now realize it, like what is this, how, what we are actually looking at it, right? And similarly we can actually plot all of these data points into this three-dimensional feature space. Fine, is
Yes,
that
sir.
clear?
Yeah.
But what is the problem here, or not problem, uh, so what to do with this data points, right? So we don't have the labels, so there is nothing I'm going to predict here, right? Let's say this is the data point, this is the data set which is given to me. What to do with that, right? So again, that's a basic problem. But look at it this way: unsupervised learning is a pre-processing step. Can I say that, let's say unsupervised uh, learning might be, okay, I'm just saying might be a pre-processing step. I'll tell you what is this mean. Step 2, supervised learning. Okay, I'll try to say about you. So if you guys have gone through MLT lectures, you might be able to recognize this. If it is not, that's not a problem. We'll try to understand what it is, right? Suppose you have you have the images. So there is a very important example which is called eigenfaces. Fine. So eigenfaces is the sorry is a very famous example. What does it have? So let us say you have uh, let's say 100 images, right? 100 images of humans. Fine. What we I think some in one of the lectures I told you, right? Each of the image can be seen as the grids, right? So let us say if you have a image of a person here, I don't know, maybe face image, right? Suppose, right? And let's say these are the ears, something like this. So this is a photo or image of an image of a person. Can I, let's say if I just divide this image into grids, okay, right? So suppose this is divided into equal amount of grids. So each image or each of this rectangle, maybe we call it as pixel. Fine,
Yeah.
correct?
Yes.
And that means this image might be a combination of pixels, right? Suppose when I say this is 28 cross 28 pixel image, what does that mean? This is when I say 28 cross. So I think all of us know, right? We have our mobile phones, and it will have a camera, and every time you know, right? If you see in advertisement about that phone also, what does that say? It is having this pixel quality, right? What does it mean? In that grid or in that frame, these many pixels will be there. Is that correct?
Yeah. Higher the density of the pixels, better is the
Better
quality.
the, yeah, right. So if you have the higher density of pixels, so if you have like larger number of pixels, the better will be the quality of image. So let us say if it is uh, maybe 100 cross 100 pixels, right, of the same of image, uh, what do you think which is having the better quality?
100 by
The
100.
100 cross 100 will have a better quality, and 28 cross same photo I'm just saying, with so what is the difference happening here? This entire set I'm just actually trying to cover into like 28 into 28. So how many number of, I don't know what will be number, around 900 pixels, right? The same
Yeah.
image I'm actually trying to see through 900 pixels, which if I can see through 100 cross 100, that means how many? Maybe 10,000 pixels, right?
Hmm.
Uh, but let us say if it is a picture of an human, what are the important features in human face? What do you think?
Eyes, nose.
Ears, right? Eyes, nose, ears, maybe teeth, right? If it is a happy face, or maybe
Yeah.
some kind
Tongue.
of a
Yeah.
shape, right? Or hair.
Anything.
These will be your. So if you are able to get an outline of the image, will you be able to understand whether this, so if you have these features, right, for each of the image, will you be able to recognize whether this is image of a human or this is image of a different maybe animal, right? So if these kind of features are so that means if you have the lesser number of features also, but if they are the important features, will you be able to recognize it, right? It is possible, right? So I can actually recognize that human face with this, let's say 28 cross 28 pixels. I don't need maybe these many pixels to recognize whether this is a human face or an a dog face or a cat face, right? So I'm just talking about human perspective. What about the computer perspective? Anyway, we wanted to feed this image to computer, right? What should be your, let us say you wanted to develop an algorithm for your company or for your school, let us say. What it does is, you will have a camera the person will walk in, and you will feed the images to that camera already, right? And the task is to identify whether this person belongs to your company or not, and based on that, let's say it will open the door. Will you be able to visualize this scenario?
Yes, sir.
Yeah, like kind of a face recognition system, right? uh, we wanted to see that whether this person which is standing in front of a camera is a part of an organization or not, or whether he is a or she is a employee of this organization or not, right? If that is my task, so or maybe the task your algorithm wants to do. So what do you do for that? You will take you'll feed like a lot of images, a lot of photos of those persons into the computer. Try to maybe learn an algorithm over there. Will What you do is you just give the images and you give the labels to that. So if you labels in the sense, let us say we are not going to face recognition algorithm. Maybe let us try to understand that whether we wanted to check whether this photo is of person or a not person. Not person in the sense any other animal. Fine, that is my task. But during training, what I am doing is I'm feeding an image, and I am telling that okay, this is a image of a person. Again, another image it will be, let's say it's a dog image. Another image it's cat image. Another image is person image. Another image is person image. So that is my data set will be looking like. Now, what this task is supervised or unsupervised? Recognizing whether if I feed a new uh, photo or image, my computer will be able to predict whether it is a person or not a person.
Then it will be supervised now because I've already seen that
Correct.
this
So
is
we correct.
or
So
cat.
correct. Okay. So right. So what I'm saying is during training of that algorithm, what we are trying to do is we are giving an image and we are labeling it already, whether this is image of a person or whether this is image of a dog or a cat. Right. That is my supervised task to predict. Given a new image to predict about whether it is a person or not person. Right. That is a classification task and that is a supervised learning task. So where does our unsupervised learning algorithm comes? So while feeding these images to computer during training, what are you feeding exactly? Pixel values, right? Basically.
Yes,
So each image, if you are feeding it to, so how does computer will work? It will store those pixel values, right? Uh, is that correct?
yes,
Okay, and let us say pixel values, let's say ranging from each of the pixel will range from between, let's say it is between 0 to 255. Uh, let's say it's RGB image or grayscale image. So in this case, what happens here? But with this, let us say if you are able to recognize, or if the computer, so how many? Okay, first of all, if I store a image, what does that mean? What I'm storing here? Am I storing numbers into the computer?
yes, sir.
Right? So basically it will become a kind of a matrix, right? If how this image will be stored into the computer is like, okay, each of these pixels will have some value. Let's say it's having 25, maybe 50, 255, 254, like that, 28 times, and here also you have 28. So can I see this image as a matrix which contains numbers based on the uh, you know based on the value of that pixel? Is that correct?
Yes, sir.
Right. So what we said is, um, maybe machine is able to recognize whether it is or a human. Let us say if it is, if all the features, all the important features are captured with this number of pixels, right? Uh, so see, with this 100 cross 100 pixels, what happens is the clarity. Uh, improves, right? The clarity improves means like you are actually uh, storing, like you are actually storing more number of values, so that it will be like it will look good, right? But our, for our task of predicting whether it is a human face or not, uh, do we need all these features,
So can I
right?
have a question here, sir?
Yeah, yeah, please.
Like you just now, you told that it's 0 to 255, it can be 28 to 28. So basically, more the data stored, it is more taxing to the
Correct,
computer.
correct.
It wants lesser data.
Yeah,
What is the optimum grid pixel which will actually serve my purpose? At the other end, it will not be very big. It not be very low as 28 by 28. It may not be very high like
yeah,
100 by 100. Maybe the
yeah,
optimum is 75 by 75.
correct.
How
So
to arrive at that optimum?
no, see, that is what, like you will have to like, so you have to so there will be an hyperparameter, right? So you will have to tune it. So
Okay.
okay, what we said earlier is, what are the important features to recognize whether it's a human face or not? We
Right.
said ear, nose,
Hmm.
sorry, ear, nose, maybe hair, right? Or the shape of the face, right? Shape of the face also is an important, because human face will have certain shape than the any other animal, right? Or any tree or something like that, right? So if these kind of, maybe I'll show you that example. I'll have that one with me. If you, okay, just give me a
This
minute.
is also a function of, at what angle you are
Battery is
sitting,
low, sir. Please connect.
what is posture and whatever.
Just a minute. I'll try to give you the. Yes, that is what. So we need uh, only important features to recognize whether this is a human face or not, right? So that is what the important thing here. 1 minute. I just, if you give me a minute, I'll try to give you that better perspective,
Okay, sir.
right? So okay, just a minute. Okay, move that slides. There are like multiple images are there. I'll try to give you maybe try to show you one of the image, which is this point would be good for you. Okay, what is your okay? SVD is what kind of technique actually? Have you just try to show you possibly? Not this is not a good image maybe. Okay, let's see. Let's try to see. Yeah. Okay. So mm, this very famous example where you can actually get eigen faces. Fine. Let us. Are you guys able to see this one? This part? This image?
Yes, sir.
Yes, sir.
So okay. So what do you think about this image? This what I am showing here. How much pixels it will have? Will it have the higher pixels or like lower pixels? It might have the highest number of pixels, right? We are able to clearly identify which whose photo is this, right?
Highest,
Yes.
Uh, and what about this image on the top
lowest.
left?
Low.
It will be a low pixel image, but whether will you be able to tell that whether this is a human face or not?
Yeah,
Yes,
Yes.
right. So how it will be constructed? So among these images also, which one will you feel that is a better image to say that it's a human one? I think from here, possibly one, two, or three, you'll be able to. So what kind of features it is actually extracting it? Important features to know
eyes,
the human
nose,
face:
and mouth.
eyes, nose, mouth, maybe the eyebrows, right?
Nose.
But the same thing is here. But can we surely say that whether it is a dog image or a monkey image or a human face image, right? It's
Not
it's
possible.
it's it's not very clear here, right?
Hmm. Hmm.
Possibly it is the lowest dimension image, right, of the
Hmm.
same. So if you just increase the dimensions, right, of that image. When I say increase the dimensions, what I'm trying to say is,
Pixels.
let us say pixels right now. Until we understand it properly, let us try to say pixels, right? But here if you see, like if you understand it properly, I think for my task of identifying whether the image is of a human or not, I this image might be useful, right? This image might be, it's fine, I think, right? Or maybe we can actually go for this, or maybe at max this. What happens if I go with this? We are able to do that task properly, right? Whether we will be able to understand that it's a human face or not. Another important advantage of this is what? it will be, so we have to process, or the computer has to process on the lower memory, right? Because each of the pixels actually we are storing it. We can do the task with this image also, or we can do the task with this image also. So what we do with the PCA is that we try to reduce the dimensions of the data, and then maybe we use that reduced dimensional data to, to do our downstream tasks, which are maybe supervised learning tasks, right? I think, if you are you guys able to understand it?
Yeah,
Sir,
yeah.
one question here.
Yes, yes.
The photo images which you have seen
Ah,
shown, just 1 second. Take that. The left hand corner
mm,
top, which is very hazy, and the extreme right,
mm,
bottom right,
mm.
they're just two extremes. One is the best, another is just an average. So can we say that dimensionality reduction of uh, the top one
Ah.
is it is higher, and whereas number of dimensions which are reduced is quite less in the bottom one, isn't like that?
May see here, there is no reduction in the dimensions. It's like, it's, let's say it's a full image, right?
We,
Full image.
With
we
Because
can
whatever
say,
the dimensions
we
it
can
is
say the
having.
losses in the left top is more than the losses in the right top.
Losses we can't say possibly, but okay, let us say loss. But
so you are
generally, what happens
compromising on the
is,
dimension, isn't
yeah,
it?
we are
Say
compromising on
there
the
is a
dimension.
1,000 features. I'm just for the argument's sake, I'm
Yeah,
discussing.
yeah,
1,000 features, we have reduced it to say 50,
50.
and this one, yeah. So that is what is the reduction what has
Yeah,
happened.
that is what the reduction is happening, and
Mm.
that kind of reduction actually we do using the PCA, because we don't want like all the 1,000 features to identify whether it's a human face or not, right? See, we can do the same task of identifying whether it's a human face or not with, let's say, with 1,000 features also. But what it will happen, two things it will happen. It will be computationally expensive, right? Because your storage will be higher, then you will have to do the computations, right? uh, and again it will be expensive. So if I can be able to do the same task by using the low dimensional data, what does that mean? We use with the, let's say, there were like 1,000 features, and if I can be able to do with the some loss of information with the lesser dimensional data, uh, if I'm able to do it, right, it will be better for me, right? Correct? Because that is, again, that is our, if you are a computer scientist, that will be your goal, right? Your computer be, what happens, what will you able to gain? One thing is it will save your time, another is like it will save your cost, right? It will be efficient one, as well as it will reduce your cost of computation, right? Because each time if you do the computation, it will, if you wanted to process the large dimensional data, it will take time also to process the data, also it will cost you more, right? So PCAs, what does PCA do? It will do dimensionality reduction. Now the part is how to do it, right? How to achieve it, correct?
Yes, sir.
Fine. So this was the theory behind, like this was the theory we wanted to understand. Now we'll try to see through uh, mathematical background. Right? So suppose, uh, what does that mean? Okay, again I'll try to give you the simple. So let's say you have two features, three features: height, weight, and let's say height plus weight. Okay, and now you have, let's say, uh, training examples. Fine. Suppose 100 examples are there. For any kind of grouping or any kind of clustering, let us say, uh, do I need all these three features, F1, F2, and F3? Can I throw away the third
Height
feature
plus,
and with
height
only,
plus weight is how it is a feature. It is not independent feature. It is dependent on this both.
yeah, but let us say somehow you have gathered the data such that I'm taking this height plus weight also as a feature. Fine. You have gathered the data. So if I throw away that feature, since it is, again, see, as you said, it is dependent on F1 and F2, right? Uh, if I am able to throw away that feature and if I somehow use these two
Okay.
features only, can
Okay.
I be able to achieve the same task?
Okay.
Right?
Yeah.
I'll be able to do that. So initially my data was in how many dimensions? X1 was in
Three.
three dimension, but actually my X1 was not lying into three dimensional space. It was lying in lower dimensional space, right?
Yeah.
Basically, right? Because the third dimension which I'm getting, the third feature, that is not important, right? Or maybe that is not independent of both like above two features, right? So actually my this is called as my data is lying in the lower dimensional subspace, and if it is like that, then uh, how to process with that, that process or that algorithm is of PCA. Okay, so what we do is, if your data lies into a low dimensional subspace, PCA what it does is it will provide you an algorithm to transform your data into higher dimensional space to a lower dimensional subspace. Is that fine? Right?
Yeah.
Okay.
Yeah.
So how does it should be actually we should do is this. I think all of us have learned about projection of the data, right?
Here, component, principal component analysis in the component means the dimension of this features. Is it?
We'll see that.
Okay.
Not dimension of the features. Actually, they are the uh, eigenvectors, basically, which are the combination of the data points. You will learn more about it in MLT. It's like very detailed explanation is given there. Here we'll try to understand uh, because this syllabus for MLF is only to
Mathematical part.
yeah, like linear algebra, or maybe it's not only one dimensional. Uh, so okay, let us say this is your data. Fine, this is your data set lying here. Uh, we have learned about uh, we have learned about the projection of the data set, right? Previously, projection of a data point. How does it look like? Let us say this was point B and this is your vector A. What is the projection here?
A transpose B by A transpose A into A.
Sure.
Hmm?
What are
Sir,
you
what
sure
was
about
the
it?
question?
What is the projection of B onto projection of B onto vector A?
A transpose B
Hmm.
divided by A transpose A into A.
So this will be your so let us say I'll say that it is P times A, some P times A, or suppose let's say C times A. So what is
Yeah.
the value of C?
C is A transpose B by A transpose A.
Right?
Yeah.
That is what we have learned, right? So it's a this is the projection.
But sometimes we see that B transpose A is also there. Is
There
it?
is no. B
When the
transpose.
because the dot product is dot product now. So there the dot product is commutative. So B transpose is also valid. I have seen somewhere. Sir also told
B transpose A.
it is a dot product. Now A dot
Yeah.
product. Is
Okay. Yeah. Okay. Fine. Then.
it
That
correct?
should correct. Correct.
This is
Dot
nothing.
product is commutative, right? That is
Hmm?
fine. Dot product is commutative, na? If
Yeah.
A transpose B equal to B transpose A, right? So that
So
should be
we
fine.
can do it, no?
Yeah, that should be fine.
Okay, fine.
Okay. But this is the concept actually we are using here, and so okay, what do you think about this data set? Okay, let us try to okay. First of all, this is a representation learning. So let us say you have these data points. First of all, we'll try to understand this part. You have these data points, right? You let's say these data points. Okay, I'll take 4 data points, and I'm showing you the values of these data points. Say 1, 2, 4, 3, 6, 4, 8. Okay. x1, x2, x3, x4. Okay. What each xi, what is the dimension of each xi here?
2.
2, right? Uh, so currently how many what, like how much amount of memory I need to store into the computer, or like if I wanted to show this data points, how much amount of memory I should be able to store? So suppose, okay, suppose each number it will take 1 byte to store. So how many bytes we need to store here?
4 bytes. 4
Eight,
bytes.
right? How many numbers we are having here?
Okay, okay.
8, right?
8.
In total we are having 8. But what is the commonality between this all those 4 points? Can I say that all these data points are actually lying on the same line?
Yeah.
So if I just, is it okay for me if I write this data set like this? Uh, suppose it is 1, 2, 3, and 4. Can I store like this data point or all this data set? What I'm doing here, these are the coefficients, right? And if I multiply each coefficient with this vector, can I get the same data set here? Yes, right? So instead of storing all the 8 values, I'm able to achieve this using only 6 values, right? Why this is happening?
Because it is a scaled version.
Right.
2,
So
3,
all
4
of these
is
data points actually lying on the same
same.
line, right? So that means all the data points actually representing only one line. So even if this data set is of how many dimensions? 2 dimensions, right? Suppose let's say here it is,
Yeah, 2 dimensions.
say here z1, z2, something like that, right? Okay. This data set was in 2 dimension, but but is it lying onto a lower dimensional subspace? Lower dimensions, what is the lower dimension to what I'm trying to say here is everything I can actually be represented, like all this data say, or all these data points are actually lying on the one line, right? We don't need actually uh, 2 dimensions to represent that data. If I, is that fine? What I'm trying to say is if I have all the data point sets like this, suppose you have, let's say, x and y, 2 axes. What do you say about these values? These values lying in 1 dimensions or 2 dimensions?
1 dimension.
One dimension.
One, right? Actually, all of this. So, can I able to find a new system such that, let us say this is a new coordinate system, right? And suppose this is w1, w2. If I move to some new dimensional system, now this data which was originally in R2, now can I represent it using the lower dimensional subspace which is R1? Yes,
Yes, sir.
Yeah, we can.
right. But I need to shift my or I need to change something, right? So I need to have new coordinate systems to show that, right? Now, and when it will happen is when all of my data points lie on the same line, right? Is that correct?
Yeah.
So let's say this W1 is this one, right? And these are all its coefficients. So if I'm, so that means now my data set actually lies in a lower dimension subspace. What about this data set? So let's say this is a line which is passing through origin, right? And let us say you have one more. Now I wanted this data, actually wanted, I wanted to represent, so this originally this data is in which dimensions, or where it is lying in 2 dimensions, right?
2 dimension.
Now I wanted to apply PCA, or I wanted some algorithm to apply onto this to get all this data set into 1 dimension. How will so okay, let's say this is my 1 dimension. This is W1. What is, how can I actually represent this now? Let us say if I drop proxies here. So that means if I do, if I have these projections onto this line, okay, suppose these were the original data set x1, x2, x3, x4, x5, and x6. These are the proxies. Proxies I'll, let's say, represented by x1 prime, x2 prime, 3 prime, x4 prime, x5 prime, 6 prime. So can you just say that this all the x1 prime, x2 prime, x3 prime, all these values or all these data points, are they lying on the lower dimensional subspace?
Yes.
Right? So these projections are actually onto the lower dimensional subspace, but not the actual data set, right?
Yeah.
Actual data set is not on the lower dimensional subspace, but their proxies can be, right? Fine.
Hmm. Hmm.
So let us say if I represent all of this data set using these proxies, uh, will that be the same data set, or will there be some error into this data set?
Some error will be there.
Right? And what should be its error? Whatever the error which is, you know,
Some square error.
right. So that means whatever the error happening between the projection of the data point onto this plane, or the like line, let's say in this case it's line, uh, that will be the error. But suppose if this error is minimized, right? If this is error is minimum, can I say that now if I am able to afford that minimum error, can I say that I am okay with that? Because what I am trying to achieve, if I allow little bit of error into my system, I'm able to show this data set into a lower dimension subspace. This might not be very evident here because only two dimensions we are looking at it, but suppose you have a data set which have 100 dimensions, and let's say with the small amount of error, if you are able to achieve this data set onto 50 dimensions, you will be able to uh, save a lot of cost and time, right? Is that correct? As we say, as we have seen into that eigenfaces example. Fine.
Yes, sir.
Okay. Don't worry about the mathematical part. Just try to understand what I'm trying to say. Like, are you fine with this idea? Whether this is good idea, or what do you feel? Will this be a good idea? Yes, no?
It will be more better than we project on the x-axis rather than another line.
Right. So okay, let us say if you wanted to project onto this X line, I will take just four values here. Okay, four data points, let's say, and you have this. Okay, this entire data set now it contains, for example, how many dimensions it is having currently? Two,
Two.
right? Okay, so let us say if you try to project it onto uh, x-axis, right? Fine, and these will be your proxies here. Okay. Some might say that we can actually project it onto this. Let us try to see that also.
Yeah.
Is that fine?
Yeah.
Okay. I may have another opinion that maybe I'll draw a line here. Okay. And I'll say that I'll project this data set onto this line. And projection is always perpendicular, right?
Yeah.
Okay. Okay. What is the problem in all of, okay, what is the, what should be, okay, first of all, what is the errors here we are getting here when I tried to project it onto x-axis? Where will be the errors? E1, E2, E3, E4, right? Mm, and these are the errors, let's say E1, E2, E3, and let's say whatever the entire E4 is there. Fine. all of these errors will be minimum or okay. So let's say this is W1 line. Which line is better to represent this data? X, Y, or W1? Okay, these are the errors. Fine. Let's say there is no error here and it's very little error. So E1, E2 is equal to 0 here, E3 and E4. So what do you think that which line gives me a lesser error?
W1.
W1. So should I pick W1 as uh, to represent this data set into one dimensional space, or should I pick X, or should I pick Y, or should I pick any other line apart from this? Okay, how many lines I can actually pick here? There will be infinite lines, right? Actually I can draw any amount of like any because all of these lines should pass through origin, and suppose I can have so many lines through it. What we have to pick is the line which will give me least amount of error. Is that fine?
Yes.
Right, in other words, it is called as a, like, you are getting the large amount of variance into the data set. How to show it is, okay, maybe this is not your part of this course, but without understanding I feel you will not be able to appreciate this PCA algorithm. Okay, so
Sir, one thing I could not understand. You just now told it is maximum variance.
yeah,
It should be least variance, na? Why it is maximum?
okay, I'll tell you. uh, Let us say
Because
there are, yeah, let us say
minimize the square sum of errors.
okay, I'll tell you what is the variance. You know, all of you know variance, right?
Yeah, standard square of standard deviation.
Right, within the data set, right?
Yeah, right.
So let's say you have x1, x2, x3, and x4. These are the points. What will be their variance? How to calculate the variance? Basically, x bar will be your x1 plus x2 plus x3 plus x4 by 4, and then you calculate its deviations,
Right.
right?
Right. Right.
Square, sorry, x1 minus x bar square and plus x3 minus x bar square, x4 minus square, and I think you divide it by 4. That will give
Yes.
your variance. Is that correct? It's a
Correct.
square of the deviations. Fine.
Right.
That is mathematically. Let us try to understand variance concept here. Suppose, okay, these are the two lines. Okay, now I have to pick the line uh, which is having minimum error, right? That we have agreed upon right now. Is that correct?
Yeah.
Which line do, by looking at this scenario, which line do you feel that will have the minimum error? W1 or W2?
W1.
W1,
Mm.
because let's say this is the error for E1 for, let's say, W1, and what is the error for W2? The same error, this one, right? This entire thing for
Mm.
E1. Uh, for E2, this is, let's say, this is the error, and here it will be this error, right? Similarly, this thing, this is 3. So I if I not draw this E1, E2, E3, E4, will you be able to say that which is the line having the minimum error? So W1 will have minimum error. Is that correct?
Yeah.
Right. Okay, so I'll just draw the proxies here. So this is its proxy after projection, correct? And what will be the proxies of these data points onto W2? Okay, where,
Proxy means projections.
yeah, projections. So it should be perpendicular to that line, right?
Mm.
Which one you will feel that it's this one is perpendicular here? What about this? Okay, possibly it will be here. What about this data point? This is perpendicular here. Maybe it is perpendicular like this, right? Onto this, I don't know. Somewhere here. What about this point? Let's say or maybe we'll try to understand this using the variance concept. We'll try to understand using maybe okay, maybe I'll show you one picture, but okay, before showing that, what, how can I calculate the variance for W1 now? I'll pick these data points, right?
Yeah.
And when I say what is the meaning of variance here in this case? These circular data points, if I show, the variance means they should be as away from like away from each other as possible, right? Is that correct? If you have the highest variance, what does that mean?
That are more away, the data points are more
Okay.
away from the
Okay.
actual points.
Right? Is that correct? I hope it is fine for all of you. So let's say, okay, we'll just try to look at it in this manner. If I try to project it all like this, possibly. Uh, so okay, maybe just give me a minute. Maybe I'll show you the MLT example. This is very good example there in the questions, I guess. There it is. Okay. Okay, let us see this part. These two examples. We'll try to understand this about the variance. So let us say these are the projections of this data. The blue are the data points, and let's say these are the no
Projections.
projections there. But I think there is a very nice example actually to showcase about the variance. Let me see. I don't know whether it was a part of this assignments or the question paper. Okay, it's not there. Let us try to understand. Variance concept, if you know, then we'll be able to appreciate this part. Suppose I'll draw this line. I'll draw another line here. I have okay, fine. What will be the how? Okay, this will be the proxy here. Is it fine? This proxy is here, and this proxy is here for this line. Let's say W1 is the line here, and this is the W2 line. What about W2 line? Where is the proxy? Okay, how can I say that? Maybe is this fine? Maybe
Yeah.
Yes, sir.
here, how it will look like, possibly perpendicular line here somewhere. And what about this? Can I say that it will be somewhere like this? No, a little bit far away. Something like this, right? Is that fine?
Yeah,
Yes.
sir.
Okay, I'll just draw the circles to understand it better. This is the one. Okay, maybe this, right? By looking at this picture, maybe this is not a very good picture, but What do you understand here? The W1 line will have the lowest error compared to the W2 line when I do the projections,
Yeah, sir.
right? But what about what it can be said about the variance here? Variance of these data points, the circles ones. So okay, when we say about the variance, what I try to say is the points on the line, right? So these blue points, will these blue points will have more variance, or will this green points will have more variance? What you can say about it? But okay,
Green will have more variance. Green.
green will have higher, or the blue will have higher?
Variance, sir.
Huh?
Green will have higher variance because the distance is bigger.
Okay, I think that's what I think. That's a problem having my image right. Okay, so okay, I'll try to, but maybe if I get the image right, proper image, I'll try to show you that. But okay, so actually, what happens here is the blue points, right? They will be as far as possible if you have the lower errors. Okay, I'll try to draw it, but I think you will not be able to see this difference, right? So here, the difference between here is actually, this difference is much larger actually than the this part, right? Another thing is this, if you try to see this, because distance we are actually looking at like this is much, this is actually greater than that. Maybe I'll show you some image if I get it later on. But okay, let us try to understand that. Okay, just trust me on that part. If you have less error, right, after projection, actually that means you will have the high variance. Okay, that means if you just if you project more and more points onto that line, right, you will be able to clearly distinguish between the points as your error reduces. And if you okay, I'll show you the picture. Maybe I think then only you'll be able to uh, recognize that part. But that is one part which is there when you have the lower error. Fine. Okay, don't worry about it. Maybe you'll be able to learn it more when mathematically also you'll be able to learn it more when you it comes to MLT. For our MLF portion, we have only one dimensional PCA. Okay, I'll show you the picture also, don't worry about it, but I'll have to search it a little bit, but I'll show you. What about this one dimensional PCA? What do you mean by one dimensional PCA here? Okay, I think I have, I'll show you one. One dimensional PCA is basically you are actually projecting the line onto or you wanted the higher, whatever your higher dimensional data is there, you wanted it to project onto a lower dimension subspace. That is your task in PCA. And here when I say one dimensional PCA, that means whatever your data, whatever your dimensions of the data is there, we will try to project it onto, or we try to convert that data set into a one dimensional space. Right?
Sir, are you looking for this one?
Which one?
I've shared one link.
Okay, I'll just I think it was solve with a slide, right? I
Solve with this question number 5.
yeah, yes, I wanted that one only. Yes, thanks. Yeah, I think now people will be able to push it more. That is a good example, actually, right? To understand it better. Uh, right. I think this one is the example. Maybe this one. Okay, I think this is the example. Okay. I hope you are able to see this one. So among all of these lines, which line you will feel that will have the lower error? let's say you have projected all these data points into different directions. Okay, what or which line will feel that will have the maximum variance here? But I think this also line will not show, right? It is already giving me only the data points, right?
Yeah, but the orange line will tell and speak that it is the high. It will have the higher
No, it
variance.
is definitely will have the highest variance, but it is not showing, telling me that it will have the lower error as well, right?
Yeah, this one is not about the.
Yeah, I wanted the. Okay, maybe we'll try to understand that through some proper example. We'll have to actually look at all these values, right, onto some scaled version. So when I'm trying to draw it here, I'm just actually drawing it by hand, right? So that's the problem it's happening here. We'll try to see that. Okay, let us try to understand in MLF perspective what is this PC algorithm is. So you will have given some data set into in which contains the data points in higher dimensions. What is your goal is to
Lord.
reduce it to lower dimension space. So how to do that? So you have the, let's say, data points x1, x2, x3 up to, let's say, whatever xn. So how this, and each of xi, let's say, is in d dimensions, right? Okay. uh, the first thing is in this algorithm is that you have to center the data set. Okay. Center the data set. What do you mean by centering the data set? Find out
Key
the
features.
mean vector. So find out the mean vector n by n, and subtract each of these values. So each xi as x bar, right? So if I do that, whatever I'm getting, right,
Error.
that is your centered data set. Why we are doing this? We wanted all of this data or all of these data points, or I wanted a line which actually goes through the zero vector in the sense through origin. So this is the technique which we generally use to get the data set. So we have learned it in stats, right? Uh, Whatever the data you will be having, if you wanted to change its mean to zero, what you do? Have you learned that previously?
We need to do the change of scale, which is basically,
You
reducing from.
generally, so how to change the scale, or how to make the data set with the zero mean?
So we subtract it from the mean. So xi minus x bar
Right. So
is what we.
whatever the mean we are having, will actually subtract that mean, so that you will get the zero mean. So that is what it is called as a centered data set, right? And then what you do is, so I'm just telling you in whatever is there in MLF. I'm not talking about MLT right now, because at this point of time you don't need that part. So what we get then? The second step will be finding out the covariance matrix. Covariance matrix. What is this covariance matrix? It is equal to 1 upon n summation of I equal to 1 to n xi minus x bar transpose xi minus xi x bar. Um, is this fine? What is your covariance matrix should look like? Basically, your covariance matrix will be, let's say, if I have d features, i- what it should have on the uh, diagonal. If it is, if I wanted to see it in matrix form, let's
So
say,
xi minus x bar transpose first or xi minus x bar into xi minus x bar transpose?
uh, Basically it's xi minus x bar transpose into xi minus x bar. So it actually it is a dot product. So
Okay.
this I have written in terms of uh, algebra. If I
Yeah,
wanted
both.
to write in, yeah, so it should be actually it should be xi or x minus x bar transpose into x bar. Is that fine? Now this is a matrix, right? And this is also a matrix, correct?
Correct.
So both of these are actually the similar statements. So why this is called as a covariance matrix? Because on its diagonal, you will have the variances, and off diagonal, what it will have? The variances between the features. Is that correct?
Pardon. Once
Okay.
again.
Okay. How does this covariance matrix will look like? So C will be so you will have, let's say you have three features. Okay, x1, x2, and x3. How does it look like? So can I say that sigma x1 square? Here it will be covariance between, let's say, x1, x2. Here it will be covariance between x1, x3, and this will be a symmetric matrix. So you will have covariance between x1, x2, sigma x2 square. Here covariance between x2, x3, covariance between x1, x3, covariance between x2, x3, and sigma x3 square. This is your covariance matrix. Is that fine? Okay, so your diagonal entries will be your variances, and off diagonal entries will be covariances. Uh, that is your basically the covariance matrix. How this will come is, I think it's the part of MLT, not it is mentioned into MLF. But yeah, it should be there, but it's not there unfortunately. So I don't know. You will have to go through this. I'm just trying to give you the understanding of it, but at this point you can just say that this should be like that. Okay, this will be your covariance matrix. Now the next step will be what? So so everything is actually proven in it's already given, all the proofs are given into MLT about this PC algorithm. In MLF, what we are trying to do is, here we'll try to solve the example, that's it, or we'll try to understand it. So the eigenvector, right, eigenvector is that direction which gives the minimum error, right? And that is the direction of, and that is what we call it as the principal component. So if you have let's say you have 100 dimensions, and if you wanted to reduce the data into 50 dimensions, so you will have 50 top 50 eigenvectors. So when I say top 50 eigenvectors, what does that mean? Or okay, top 50 eigenvectors of what, right? So eigenvectors are of what? They should be of some matrix, right? And that matrix will be a covariance matrix. So in general, PCA is uh, what we actually concerned about of 50. Let's say if I have 1000 features or 1000 dimensional data, and if you wanted to reduce it to 50 dimensional data, so this data actually, so 1000 features, if you project it onto the 50 eigenvectors, right, top 50 eigenvectors, what do you mean by top 50 eigenvectors? If what is the dimensions of C if you have 1000 features and let's say n examples? uh, let's say, okay, one more part I will try to understand here. Let's say you have capital D features and small d features you wanted to project, and let's say you have uh, n data points. What do you think should be the dimensions of covariance matrix? What is the dimension of matrix X? We have seen it, right, previously.
Matrix is 2 into 4, na? Or 4,
Okay,
4 into 3.
what about this here?
I think it is 4 into 3.
So it should be 4 rows and 3 columns, right? And
Right.
and let's say if it is n here and it is d here, what is the dimension of this matrix? N cross d, or
That's 3.
N cross D.
right? But generally, how do you write this vector x1? Like this, in a column format, right?
Yes.
So if I have the how does this will look like? Sorry, d cross n. So what I'm having here, let's say these are the vectors. How many vectors it will have? N vectors, right? Can I say that we have d features along this side and n examples on this side? So basically we take this matrix, right? Are you able to understand this? Because we take the vectors in this format, right? X1 is R3, x1 is in R3. So how do you plot these data points into three-dimensional space? And if I add all of this x1, x2, x3, because my matrix X will be what? Matrix X will be like this. X is the like it will have x1 here, x2 here, x3 here. Is that fine?
Yeah, yeah.
So what is the dimension of this now? And let's say each of xi is in RD. What is the dimension of this data set?
3 cross n.
D cross n. Is that fine?
Yeah.
Now it makes sense, right? Each of this data point, I am putting it into a matrix, right? Because each of the data point is a vector. Now all the vectors I am combining into a matrix, fine. And each of the data point is in d dimensions. So this the data set will look like d cross n. What was the next step? I just subtracted mean from each of this data, right? So what will be the dimension of? Oh, okay. When I subtract x bar from each of this, what will be the uh, dimension of this data set now? Will it change or will it remain same?
Same.
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 It will remain same, right? So the dimension of this x minus x bar will be d cross n. So when I say the covariance matrix is this matrix 1 upon n x minus x bar transpose into x minus x bar. What is the dimension of C? Okay, sorry. I think I have written it wrongly. It should be, this should be your covariance matrix. Okay. Now it's, tell me what is the dimension of this? Because, okay, I'll write it once more. This matrix is like this: x minus x bar into minus x bar transpose. So the dimension of this is
D cross D.
d cross n, and what is the dimension of this transpose matrix?
N cross D.
So the
D cross D.
D cross D.
okay, so the dimension of covariance matrix is d cross d. Is that fine? Okay, so if I want, so what I said is the eigenvectors of this covariance matrix will be your, so okay, let's say if it is a d cross d matrix, how many eigenvalues it will have? Like maximum number of eigenvalues it can contain.
D.
D, right?
D. D.
So the maximum number of eigenvalues will be D.
D.
Okay. All of you agree with that part?
Yes, sir.
Okay. If you have D eigenvalues, and then that means I will have corresponding D eigenvectors, right?
Yeah.
Yeah, if they are distinct.
If they are distinct, or right. But suppose if I say that out of all of this, so if I find out its eigenvalues, right, and I don't want all of these eigenvalues, or I don't want all of these eigenvectors corresponding to that. I'll just require, why I don't want is, let's say if this is a sparse matrix. Okay, don't worry about that part. But let's say you have d eigenvalues, and among this d eigenvalues, let's say you have the 5 eigenvalues which are 0. Fine. I don't want those eigenvalues to be considered. If I don't require those eigenvalues, what will be the dimension of my or okay, then what will happen to my data set then? The data set now, it will be a data set of
Lower dimension.
or the data set which is low dimension, that's correct. But now how does it look like? Uh, so visually it should be
It will look like a single value.
right. So maybe what I'm trying to say here is, suppose you had this data set, okay, this three, so you have, let's say 4 data points, okay. These are the projections on the, let's say this w1 is eigenvector, uh, w1 will be eigenvector, then what is this? These are all the, these are will be, these will be the data points, right? But these will be, these are also will be the vectors, is that correct? But these vectors are in lower dimensions, okay. Initially your data set was in 2 dimensions. Now when I project it onto w1, my data set will be on in 1 dimension. So now this entire data set, we have got into 1 dimension, that is fine, like in the lower dimension, that is fine. And how many eigenvalues this covariance matrix should have? Ideally it should have w1 and w2. We can actually project this data set onto w1 also, right, as well, correct? But what we are doing here, we are just ignoring these values. We are actually ignoring, saying that these will be the errors, and we just wanted to keep only the w1 here, and by using that w1 we'll try to reconstruct the data set. What do you mean by reconstruct the data set? We'll just take these data points for my further calculations, or maybe for, let's say, for supervised learning tasks. Fine. How to do that? Mathematically, let us try to see this. So you have this covariance matrix here. What you do? You just find out its eigenvalues and eigenvectors, right? Keep only whatever the, let's say, keep only those eigenvectors. Generally, we keep eigenvectors or eigenvalues which covers 95% of the variance. Uh, that is the general practice people do. Whatever the remaining 5% variance will be, actually its highest eigenvalue will be corresponding to the highest variance in the data set, okay. Okay, but I think we don't want to go into the details right now, but we just keep only those eigenvalues which will contribute more. That means we'll have, let's say you have, after this covariance matrix will have, suppose these eigenvalues 5, 4, 3, 0, or maybe let's say 0 0.5, 0 0.1 and 0, right? So what we do is we keep only the top eigenvalues, and we will not consider the remaining eigenvalues. We just be concerned about these eigenvalues and the eigenvectors corresponding to it, and then we take that data set and try to get the projected data points, right? Whatever the data points will be, we'll be having. Fine. This is the practice we do in PCA. Let us try to see it through an example, because I cannot explain it more here, because that's what it is having limitations. But try to see through the example. So we have only uh, so let's say you have this data set, okay. What I said is, what should be, so okay, each of this will be the data points, right? What are each xi here? What are the dimensions? 2 dimensions. What is the next step in this algorithm? Find out its mean vector. So what will be the mean vector? By 3. Is that fine? So can I say that 1 by 3 minus 1 plus 0 0 plus 1 1. This is a step which is about the centering the data set. What is the mean vector here? 1 by 3 into 0 0. Right, so basically it is 0 0 is x bar. So what will be the centered data set now? It will be, let's say, x minus x bar, right? So basically it is the same data set since it's already centered, right? Your mean vector is already 0 0, so this is the centered data set. So let us say it is actually the same data set right now. This is minus 1 minus 1, 0 comma 0 and 1 comma 1. What is the next step now? To find a covariance matrix. So covariance matrix in this case will be 1 by 3 x1 minus, okay, I'll write it down here. It should be like this: x1 minus x bar into x1 minus x bar transpose plus x2 minus x bar into x2 minus x bar transpose plus x bar into x3 minus x bar transpose. Fine. So what it should be here? Here it will be minus 1 minus 1 and transpose will be minus 1 minus 1 plus this 1 1. Here it is 1 1 plus, okay, sorry, it should be 0 0 right here. Here it is 1 1 1 1. Okay. What is this values come out to be? So what is this multiplication? This is 2 cross 1 into 1 cross 2. So it will be a 2 cross 2 matrix, right? And that should be equal to this. Here it is 0 0 0 0 plus 1 1 1 1. And one of the important property about covariance matrix is that it is always the symmetric one. So here it is 2 2 2 2. This is my covariance matrix, right? Okay. What is the next step? Step 3 will be
To find eigenvalues and eigenvector of the covariance matrix.
right. So to find, first of all, let's say to find eigenvalues. So what will be the
How
eigenvalues?
did you get this 2 2 2 2?
Huh?
This 2 2 2 2? How did you get it?
Here.
Okay, operation of this. Okay.
Right, so it's like you just multiplied this, you got this part, right? This matrix after the multiplication of this
Yeah, then 2.
0 and then it will be 1 1 1. So if you add all of this, this is your covariance matrix. Okay. The how to find its eigenvalues? So basically
Characteristic equation 2 minus lambda, 2 minus lambda. Lambda is equal to 2.
equal to, let's say, 0, right? So it will be, and 1 by 3 is obviously there. We can actually use 1 by 3 here itself. Like you can do like 2 by 3 by, right? 2 by 3, 2 by 3 and 2 by 3 here. That is also possible. Or else you find out the lambda values here and then divide it by 3, right? Or multiply by its coefficient 1 by 3. So here this will be 2 minus lambda, 2 minus lambda minus 4 equal to 0. Determinant of this, right? And it will be 4 minus 2 lambda plus lambda square minus 4 equal to 0. So it will be lambda square minus 4 lambda equal to 0. So what is the value of lambda? Lambda equal to 4 and 0,
Zero, yes.
right? Because this equation can be written as lambda into lambda minus 4
Yeah.
to 0. So either lambda is equal to 0 or lambda
Oh.
equals to 4. So the highest eigenvalue is which one here?
Oh.
4. But this is not the correct answer, right? It should be divided by,
4 by 3 because
yeah,
3.
yeah. We have to multiply this. So actual eigenvalues of this matrix will be 4 by 3 and 0. Fine. These are the eigenvalues. Done. We'll have to find out its eigenvector. So what will be the eigenvectors here? So for lambda equal to 4 by 3, what should be the eigenvectors? Your matrix was 2 by 3, 2 by 3, 2 by 3, and 2 by 3, and minus lambda I. So it will be minus lambda, right?
Yeah.
And and if I just substitute lambda here, it will be this one into x1 x2 equal to 0 0. What is this? It is c minus lambda I into x equal to 0. This is characteristic equation, right?
C, yeah, yeah.
C is your covariance matrix.
Yeah.
Okay. Okay. So this will be what? Minus 2 by 3 plus 2 by 3, 2 by 3 minus 2 by 3, x1 x2 equal to 0 0. So so if I do the um, Gauss elimination method, I'll get minus 2 by 3, 2 by 3, 0 0 here, and x1 x2, right? 0 0. If you don't do also is fine, but if I do also is fine. So with this, what I'm getting here, minus 2 by 3 x1 plus 2 by 3 x2 equal to 0. This is the equation I'm getting. If I just boiled it down again, so it will become x1 equal to x2. So for any value, like if you substitute the value of x2 as 1, so your u1, I'm just calling it as the eigenvector. So u1 will be 1. If it is 1, it will be 1, right? So is it 1 1? Right? Because x1 is dependent on x2. So my first choice of x2 will be, let's say, 1. So then it will be 1 1. But what will be, we should be considering the unit vector along this direction. So what will be the unit vector? We'll have to
1 by root 2.
Yeah, we'll have to divide it by its norm. So norm of u1 is, it is root of 1 square plus 1 square, which is root 2. So if I write 1 by root 2 1 1, it is a eigenvector corresponding to which eigenvalue?
4 by 3.
4 by 3. Okay, what will be the eigenvalue? So actually, so this is one dimensional PCA. That means we should be caring about only the single dimension, and that important direction will be this direction, which is corresponding to the maximum areas or corresponding to the maximum eigenvalue. Okay, that's let's keep it aside. Let's try to find out. Sorry. So let's try to find out.
For an eigenvalue, only one eigenvectors are possible, or more eigenvectors are also possible?
Sir, no. If the eigenvalues are distinct, okay, you're saying that whatever the
What happens in the case, this is the 2 by 2 matrix, suppose a 3 by 3 matrix, then we get sometimes we put the value, suppose assume x2 is equal to 1, then x1 is equal to something and x3 is equal to something. In that case, which one we should take?
Because so that's why for the if you just okay, so okay, can you just tell me whether okay, this is now here u1 equals to 1 1,
yeah,
u1 equals to 1 1,
yeah,
u1 equals to 2 2,
yes, this I understand.
5 5. Are they same or are they different?
No, these are the same.
Same, right? So that means these are the same eigenvectors.
But
okay, what is your question?
In some cases, I have seen that two values comes. Suppose 1 1 is there, that another eigenvector we get corresponding to the eigenvalue is not the scaled version of the eigenvector we are getting. In case of complex vectors also, or 3 by 3 matrix also. Is it possible or I'm wrong?
No, it should not be like that. So it should be the scaled version. So it should be a scaled version of your unit eigenvector. If you are getting something differently, right, then there is a problem, right?
Okay.
It should be
It means one eigenvalue will have only
one
one.
eigenvector. Yes, yes, that is for sure.
That
That
is
is not,
sure, no?
yeah, yeah.
Okay, then I will put the
If
example.
it is a
When
repeated eigenvalue, right?
I will get, then I will put the value.
Yeah, yeah. So let's say if you have eigenvalues like this 0, 0, 4, fine.
Mhm.
So you will have different eigenvector for this 4, fine.
Mhm.
You have the same eigenvectors for this 0, 0, or you may have the different eigenvectors for this 0, 0, fine. But it is possible that if you have the 3 eigenvalues which are, let's say, 0, 0 here, they may have the same eigenvectors.
Yeah, that is possible. That
Okay? Again, they may have different eigenvectors, but
for 4,
yeah, but
only
if you
one.
but if you have this, let's say 0, 1, and 4 as the eigenvalues,
Yeah,
they 3 will have different eigenvectors only.
and that will be unique.
Yeah, they should be unique, right?
Okay.
Because the eigenvalues, what it does is, what is the equation of what is the eigen equation here? As
Ax minus
let's say
lambda
ax equal to lambda x, right?
x.
So if your lambda is changing, right? So it should change your eigenvector, right? Otherwise, then this equation will not hold, right? Is that fine? So if your eigenvector is same here for like same both of the eigenvalues, let's say different eigenvalues, if your eigenvector is same, I don't think it will give me this that kind of feeling there, right?
Okay.
So I think it shouldn't be like that.
Okay, fine.
Okay,
I will
fine.
see
So
that. I will see
yeah,
that.
okay. Coming back to our problem, what should be your u2? U2 will be the eigenvector corresponding to another
Zero.
eigenvalue, which is 0 here.
Zero.
And so our initial matrix was what it was like
3
2 by 3,
cofactor matrix.
2 by 3, 2 by 3, 2 by 3. Can I say it is when I subtract 0, 0, it will look like this only, right?
Yeah, yeah.
So what is the equation if I, so it will
X1
be
is
2
equal to X2
by
is
3. Yeah. X1 equal to X2 or X1 equal to minus X2?
no, X1 is equal to minus X2.
So it will be X1 equal to minus X2.
Just one question here, you have usually I think it is mentioned we should take the maximum lambda, so you should not take the lambda which is 0.
Correct. That is true. So for PCA, why we are actually working here only one dimensional PCA. So we have to correspond. We have to span it for only the
Only, yeah, lambda is equal
right,
to 4,
right.
not
But
for
yeah, but when you wanted to reconstruct the data, right? Reconstruction of the data.
okay.
So
Then that time you have to use it.
you have to use it if your data set is not centered. If it is centered, right? Okay, I'll show you how it is. Fine. So what is the u2 here? Will be, let's say it's my 1, here it should be minus 1,
Minus 1.
and the normalized version will be 1 upon root 2. Is that fine?
It can be 1 or minus 1 also.
Yeah, that is possible, right? Any coefficient. So it will be like, let's say it will be c times u1, right? Or c times u2. Fine. So c times u2 is
Minus of
minus
yes.
1 times of u2. So it
Yeah,
will
yeah.
just 1 and minus 1, but it is the same thing, right?
Correct.
So I'll summarize it here. So for our covariance matrix, we had two eigenvectors corresponding lambda equals to 4. You have u1 as 1 upon root 2. I think it was 1, 1. And lambda equal to 0. You have u2 as 1 upon root 2, 0, 0. Actually, there is a very nice explanation of about this PCA in MLT, right? But I cannot show it here because again, it's not the way here it is taught. So I cannot go into that many details. But fine, not an issue with that. What is the next step? We have to find we have to see the projected data. And what is that projected data? So these will be the new points, right? They are mentioned by x1 tilde. So okay, what we have seen, right? I think I'll go back again to our original problem.
When we reach to the calculation, we forgot the what we started.
Yeah, it's okay. That's I'll just again come back here, right? So that is okay. Let us say these are the u1s. Okay,
Yeah,
correct. This is
yeah.
u1 and this is u2, right? These are the two eigenvectors. Now we had this. Let's say these three data points in our hand. This will be the projection. So let's say this is x1. What is the projection of this onto this part? Is it x1 transpose
One thing more,
u1?
we get the eigenvectors after calculating that.
Uh,
That are always orthogonal, no?
yeah, they always be orthogonal to each other.
Okay. Okay.
Yeah, right. So here, what do you think about this? Is this a projection of x1 onto u1?
Yeah.
And what will be its vector?
Mm,
So this is the data point,
multiplied by
which is this vector.
divided by u1 also. Okay, unit vector. Yeah, yeah.
Fine. Is that okay?
U is the unit vector, no? Yeah, yeah. Correct.
Right. U is the unit vector. So
That
what?
way the denominator is 1.
Correct. So this is the point, right? What about this point x2? X2 will be x2 transpose
Transpose
u1
u1
into
u1.
u1, and similarly x3 transpose u1 into u1. Is that correct?
Yeah.
These are the projections of x1, x2, and x3 onto u1.
Yeah.
If your data set is not centered, in this case we have just,
That line once again, sir.
yeah.
So it is coming out to be, it is x1. It is x1 1 transpose e1. That's a
Right.
scalar into the vector e1.
Okay, I'll try to show you. So this data point is here, x1, right? But this data point, when I say it's a vector, right?
Correct.
And this vector goes through, let's say, because vector always goes through 0 point. Is that correct?
Correct.
So suppose this is your x1, and suppose this is my line u. This line represents u1. But where is this unit vector u1? Basically, let us say it is here. Okay, fine. How to represent, and what is the projection of this x1 onto this u1? This is the projection.
Correct.
So basically, this is the projection. So this projection should be some constant of u1. Is that right? Some constant of u1. But what is this constant? Basically, it's a projection of x1 onto u1. And what is this projection? It is x1 transpose u1. We have learned it, right, before.
Correct.
I think somewhere I think I also have discussed. But
this is a scalar. This is a scalar value.
this is a scalar value.
It is a k.
Yeah. And what is this vector now? Because this is also point. What is this vector now?
Multiplied by the unit
k
vector.
times u1, right?
K times u.
Basically, it should be like this, right?
Yeah.
And it will similarly happen to all the data points. So your x1 projection, projected data point will be what? Let us say we we say them as a x1 tilde.
Yeah.
And what is its now? Basically, it should have
X1
x1
transpose
u1. This is
u1
my projection, right?
yeah, into u1.
Into projection. This is my projection. Projection of x1 onto u1, right? And basically, this is your vector.
Yeah, vector.
And this is a scalar, right? This projection is a scalar. I hope it is understandable.
Yeah.
There is another part to it, which is actually it is you given into while solving this problem into this syllabus of MLF, which is x. We have to add here x bar transpose u2 of u2. Okay. In this case, in this our example, what is the value of x bar?
Mean of the
And what was it came out to be?
x bar
Was this?
X bar was mean, no? X bar is the
mean vector, right? It was not it this one in this example.
It is 0, 0.
Yeah, we have calculated initially, right? This was my data set -1, -1, 0, 0, 1, 1. And you just see -1 plus 0 plus 1, it's 0. -1 plus 0 plus 1 is 0, right? It's a 0, 0 vector, correct?
Mean is 0.
Mean of the data set was 0. That means what? It was a centered data set, right?
Okay. If it is not centered, then x1 minus x bar, x2 minus
So
x.
okay, how does this data set will look like? Shall we draw it onto this two dimensions? Where you will feel where is this -1, -1? Okay. Can I say that this is the data point -1, -1? Where is 0, 0? This one.
Yeah,
Where is
center.
1, 1? This one, right?
Yeah.
So this actually it's already onto this line, right? So basically, if you try to understand here, my transform data point will be what? Will be the same data points, or will be different data points?
Okay, there will be no projection required because the projection is itself the line, right?
Right. So that is our understanding through this visual purposes. But we should actually get this through whatever we are actually doing here, right? So what is my x1 transpose u1? Let us say what is my x1 data point? -1, -1, right? And what is u1 here? This one. What is the projection here of x1? This is x1, right? I'll write down here x1, x2 was 0, 0, and x3 was 1, 1. Fine. I'm just writing out again. U1 is 1 by root 2, 1, 1. U2 is 1 by root 2. I think it is -1, 1, something like that, or
minus
right?
1, 1, minus 1.
That's fine. Is that okay? So what is the projection? Let's say first projection. What is the
U3?
U3 is not there, no? Only two. So this data set, you see the covariance
Eigenvalue.
matrix. Sorry?
Only two eigenvalues, so two eigenvectors.
Yeah, only two eigenvectors. You can't have U3, right? We already, your covariance matrix was a 2 cross 2 matrix. That means it will, maximum how many eigenvalues it will have? 2. So you will have only two eigen directions, right? And again, this eigen direction is corresponding to lambda equal to 4, and this is corresponding to lambda equal to 0. So when we consider the one-dimensional data set or one-dimensional PCA, we should omit this. But when we should be able to omit this? When your data set is already centered. So currently it is centered. So what is x1 tilde here?
X1 transpose.
So what is x1 transpose? -1, -1 times u1 is 1, 1 into 1 upon root 2.
Yeah.
Or maybe I'll write down 1 upon root 2 inside. However you wanted to, right? And this is my projection times u1.
U1. 1 by root 2, 1 by
and plus x bar into u2 plus
that is 0.
but that is 0, so I'm not using it
because the data is centered.
And now you just see that what is this value here? So this is 1 cross 2 and this is 2 cross 1, so will it be a scalar value?
Yeah, scalar
Yes.
value.
And what
it will always be a scalar value because of this.
Yeah, so what is its scalar value here?
There will be 1 minus.
So can you show the formula here, because you have mentioned u1 and u2 both? It should not be only u1.
Yeah, let's say x bar times u2, x bar transpose u2 into u2.
Should be x bar transpose u2 or x bar transpose u1?
Yes,
because
no, u2.
So this portion is u1, this portion is u2.
Yes.
X bar portion will take u2, and x1 transpose will take u1.
Yes. So that is same for x2 when I calculate x2 tilde, right? x2 tilde, what is it should be? x2 transpose u1 into u1 plus x2 x bar transpose u2 to u2. So this is same for all the transform data points. You see, right? Why this is required is if your data set is not centered initially. Is that
This is
okay?
the actual shift of the data.
That is what, like, this we are actually so in, let's say, okay, what we are actually finding out here is these are the transform data points, but into the same dimensions, right? Whatever the initial dimensions are there, this is called a reconstruction. So what we did initially was we subtracted the mean vector from the data set, so we made the data set centered. But when I just wanted to so that means what I did is I wanted those eigenvectors going through the origin, but actual data was not going through the origin, right? So your the projections also should be added with some that whatever we have already subtracted, and that is what and you see your u2 direction is always perpendicular to u1, right? Where is this u2 will be? So where will be this projections of x bar? Okay, we'll try to understand here
On U1.
So okay, let me draw one more diagram for you. Okay, let us say you had this data set somewhere here. Is it a centered data set? The okay, which will you, what do you feel that is a good line? This will be the good line with the minimum error, right? Is that correct?
Which one you are talking?
Here, this one.
Yeah.
This if this was my data set, right? Is it a centered data set? Probably not.
Probably not.
Or it is not. Okay, because if I see this line is a good line, which actually is the better line, right? Suppose this is my u1 and this is my u2. Okay, but I don't want my data like this. What I do is I will calculate the mean vector and I subtract it. So what I do is I will just subtract, or I will just shift these data points like this. Fine. Now what is happening here? Now,
so that it could pass through the origin.
It has just shifted, right? Now it has shifted.
The purpose of the shifting is it should pass through
the
the
origin. Yeah. So that is what.
This is the only purpose to shift.
Yes. Okay. That is the correct purpose, right? Because we wanted our frame of reference, right, in this manner.
Passing through the origin.
Right. So let us say original data set was like this, and suppose this was your centered point, right? And when you subtracted this x bar from each of the data point, this was the centered data set was looking like. What you are doing is, when I just project all of this and get a new data set, and if I wanted to transform into the original data set, what I should do? I should add this projection, right, into all of this. Is that correct? So that what happens now? Okay, this is what the projections, right? Now if I add x bar transpose u2, which is this part, to each of them, what I'm doing? I'm again shifting back to my original data set, right? Is this idea clear? And let's say this is u1.
So here we first get the best fit line, and then we orient according.
Because how we actually centered it, right? So initially it was not on the center. Initially my data was not like centered. What we did is we just found out its mean, we subtracted its mean and get that data centered first, and then you found out its projections onto the new reference lines. Let's say it's, in this case it's u1, which is eigenvector. We get the projections onto the eigenvectors, but what happens here, like it is not where exactly my data set lies, right? It was little bit away from there, right? Because this was the baseline, right? This should be the baseline.
Yeah, that was the baseline, but
we have shifted. We just have shifted by what amount?
No,
This amount.
we do not shift that line only. We
Yeah,
shift the whole
data set.
orthogonal
Yeah, or maybe
orthogonal.
you can say that we just shift the
Right now, I'm right now.
coordinate system.
We are just shifting the frame of reference
Frame
directly.
of reference. Yes.
I'm
It is basically change of scale.
Yes.
So
Yeah. Yeah. That is what.
by by the centering amount, which is x bar.
Correct. And now again, when we go back to this data set, we have to again regain that all the values, right?
okay. And
And
here the
now
tilde we are getting the original.
it will not be original. It will be projection again, right?
Yeah,
Here
projection.
there is little bit of loss of error. It's there, right? That loss is there already. Okay, maybe I'll just final diagram I'll draw it,
Loss will be there. Loss will be there.
right? So I think this is the final one. You will just try to understand. Okay, I'll try to show you as much as possible I can do. Suppose this is the data, right? What you do is you just make it centered. Okay, how do you did that? By using the or by subtracting it, right? Correct. Right. Okay. And suppose this was your mean somewhere here, mean vector. Fine. Okay. We don't have to worry about it right now. Let us say these are the projections of this. Correct. Now this is what is this value here? Suppose this is x1. This is actually x1 plus or either x1 minus x bar, right? Because when
X1
I
minus X bar,
extracted
yes.
this was x1, this data is actually was what? It is x1 minus x bar, right? So what is the projection of it onto this u1? x1 minus x bar transpose u1.
U1.
Is that okay?
Yes.
Right. So and what is uh, x1 minus x bar basically? So how do I get it? If this was the vector and this is my
Because
projection, so it
shifting.
should be equal to x1 minus x bar transpose u1 plus error. Is that correct?
No, why it is an error?
This one while projecting this one, right? And what is x1?
X1 is the actual
Should
value.
be x bar. So let's say there was some x bar. I have subtracted here x bar. So I have to again get it back, right? So x bar is somewhere here, let us say. Correct? And its projection actually this perpendicular distance only I'm just so always u2 is perpendicular to u1. So whatever amount I have actually shifted here, right? I should be actually going back again, right? And that is what x bar transpose u2 of u2. This is the whole thing. Where is my x1 tilde is? I will not consider this e1 there. So x1 tilde will be like this. So x1 tilde will be this part. X1, let's say I'll just instead of writing all of this, let's say x1 transpose u1 of u1, right? And okay, this was the scalar times u1. All right, okay. X1 transpose u1 of u1 and plus x bar transpose u2 of u2. And if you add plus error, then that will be your exact data point.
Okay.
Okay.
Error is also there after transpose.
Correct, na? Is that correct, na? Agree? All of you are agree with this? This is little bit of understanding. Okay, you'll have to again think about again and again, and I think it will be done.
This error is same as when we calculated the sum square error. That's the same error.
Yes, yes.
So how do we be getting the x3 tilde?
So x3 tilde, where it will be, let's say this is x3 point. Okay. This is the original x3 point, let's say, correct?
Correct.
What, and this is what? Suppose x3 prime. What is x3 prime composed of? Is it x3 minus x bar? Is that correct? What is
Correct.
its projection here onto u1? x3 minus x bar transpose
u1.
u1 of u1, right? Because this will be my projection into u1, I'll get a vector, right? Fine. So now if I just summarize it again, x1 tilde will be x1 transpose u1 of u1 plus, let's say this is to accommodate my shifting of mean. x2 tilde will be, sorry, not u2, u1 of u1, because basically you are actually, what you are doing is you are projecting all these data points onto u1, and that is our point of interest, right? So everybody here, it's u1. Fine.
See, if in this earlier in this example, if the lambda there are three values, so here we got two values, 4 by 3 and 0. So suppose we get three values,
Let's
4
say
by
we
3.
have three values. That means you will have three eigen direction.
So you'll
It
have
will
three
be
unit,
u3.
yeah, 3 unit eigenvectors.
So then in that case, it will be x bar transpose u3 of u3 of u3 plus
Okay.
x bar transpose u3 of u3 plus x bar because we are caring about only, this is one dimensional PCA, right?
Okay.
So we are just caring about the projections onto u1.
And okay, fine. And this U1 will be the for corresponding to the
Maximum eigenvalue.
maximum eigenvalue. Correct. Okay.
In
Okay.
our code, only one dimensional PCA is there.
Yes, for MLF it is one dimensional PCA.
Okay.
For MLT it is like everything. So
Okay.
and I think that is a better perspective to understand it. But it's okay.
In that case, the projection on the U2 also will be counted, right?
Where if you have more dimensions, yes, then you will actually your data set will be okay. So if you try to understand it in this way,
Just for knowledge.
just if I wanted to show you, let us say you have these data sets, okay. So consider now it's a centered data set.
Yeah.
Okay, you have this u1, you have your u2 here, okay, corresponding to, let's say, two directions. So this projection here, right, of this, let's say, x1 data point, what is the projection of x1 onto u2? This one, correct? What is this projection x1 onto u1? x1 transpose u1 of u1.
Yeah.
Right. What is the projection of x1 onto u2?
x1 transpose u2 of u2.
Of u2. Okay. But now for a moment, can you tell me this? What is this vector? Where is this vector? Is this a vector? X trans x1, and this is a vector, another vector, right?
Yeah.
And
resultant.
Okay, for now, just don't don't consider about this part. What do you think about only when I project x1 onto u1? What is the error here? This part.
Yeah.
This is the error.
Yeah.
But can I say that this error is equal to x1 transpose u2 of u2? Will this with the same values?
Yeah, same value.
Right. So can I say that with the vector addition, can I say that x1 is equal to x1 transpose u1 of u1 plus x1 transpose u2 of u2?
Yeah, this is the actual one.
Right. Yeah. And we actually consider this as error, right?
Yeah.
So can I say that, let's say, x1 minus e1 is equal to x1 transpose u1 of u1. So when we consider about only one direction, we are actually throwing away this much of information, right? So now suppose you think about there is another direction u3. So what this x1 will look like then in that case? It will be plus x1 transpose u3 of u3.
Yeah.
Correct. If just try to imagine, okay. Let's say you have third more direction, and in that case, uh, this will be error for what, this data point or this projection. Think about it. So now we say that E1 is equal to this, right? But then the error in the third dimension will be actually this will be this error, right? Suppose this is A2. Are you able to understand that part? Yes, no?
No.
Okay.
Because 2 dimension we can understand. Third one.
See, okay.
3D. Yeah, I got it. That will be third dimension, no only.
Right.
U3 will be third dimension.
Yeah, that's it, right?
Yeah.
So
In
suppose
this space, then the data will go to the space, no? Right.
so let's say this is your projection, this is your another projection, and this is your another projection.
Another dimension will be there, no? Right.
So this will be actually equal to, so everything, okay, all of this will be actually so
the whole frame of reference changed.
Currently what I am saying is, I'm trying to say is, all the projections, if I all these projections of x1 onto all these eigenvectors, they should be equal to x1, right? If I add all of this, they should be equal to x1, correct? So I wanted to choose how much of information I should throw away. So if I just wanted to take the information up to this part, that is one dimensional PCA, what I am trying to here is, I'm trying to lose here this part. Is that correct?
Means dimension also will choose according to our need.
Yeah. So because how much it is contributing to your so suppose most of the information is actually into one dimension, right? One dimension subspace. I will throw away the other 2 dimensions information, right? So if you have multi-dimension, 100 dimensions you are having, then
if you recall that picture, in that case only 2 or 3 eyes, nose, and this was there. The only 3 dimension will be taken. Right? Is it like that, na?
Yeah, correct. So basically, if I project x1 onto all 100 dimensions, because you will have 100, let's say, eigenvalues. So how does it will look like? X1 will be like all the projections up to, let's say,
u1, u2, u3 up to 100.
Sorry, x1 100, u100, right? Of u100. But if I wanted only top 2, I'll retain this top 2 and I'll throw it away the remaining. That is the essence of this exercise.
Computational saving will be there, right?
Correct. Because you don't need to compute all of that.
Right? Will be solved with that.
Right. So so I think that's
but in
about
some of the cases in the higher accuracy levels, it must be, I think it could have been calculated, right?
Higher.
So accuracy level is high, like in the rocket science or like that.
Then you will have, so what is your requirement, right? So accordingly you will have to choose.
Yes, we need, then we can do that, right?
Yes. If you want entire, because if you can't throw away all the information, in that case you don't have to go through PCA. PCA is not compulsory technique, right? It is required when we can do it with the like little bit loss of information.
Lower in the case of lower accuracy.
Correct. Okay. So this is about the PCA theory. In the next session, we'll see about the questions behind it.
Okay. One.
Right.
Yes.
Okay. Don't worry about it. So whatever you understood it's fine. Whatever is not, I tried my. So I didn't go into MLT also. I didn't stick to MLF also. I just tried it a little bit differently. I hope you understand gist of it at least, like what we are trying to
No,
do
no,
here.
we got it because I was afraid that I will how because we could not do that with six, no, with six. So, but it's not related to that.
Yeah, it is different, like completely different part.
Yeah.
Okay.
Yeah.
So whatever. So I think now you should go through the content again. And after that, maybe if you have any doubts, we can actually discuss it later on.
Yes, sir. Okay.
Right? We have the revision sections also when we'll discuss again if you want. Fine.
Okay, sir.
Okay, guys. Okay. Thank you for joining the session today. Good night.
Good night, sir.
Good night.
Right, sir.